questions, about your particular grade, that's best served through email, only because sometimes in order for me to run the numbers, I need the time to sit down with my spreadsheet and look it over. Getting a number just off the top of my head isn't really practical. Also, that first technology assignment that we did was designed with the purpose of you being able to compute your average at any point in time. So now you have some data. That data can go into, if you go back to your first technology assignment, you could take the data from this course, all your grades, pop it into that tech assignment, see where you're at, and start playing around with the numbers and see what you would need to get, play the what if game, see what you need to get on the final exam in order to get the grade you want to get. And if you're ever in doubt, just shoot me an email and I'll confirm it with you. All right. So on to the practice final. Number one, which of the following is not equivalent to f of x minus g of x dx, all right, over the interval of 1 to 2. All right. So it's a check all that apply, which means that there could be more than one. So you just got to be careful about that. Basically, for a question like this, you just got to kind of go through every property that you recognize and see how things would play out. Now, one thing that I noticed is that the bounds of integration in some of the choices, actually all the choices, are backwards. All right. We can reverse the bounds of integration as long as we negate the integral. All right. So this would be equivalent to negative the interval from 2 to 1 of f of x minus g of x. All right, so this is equivalent. All right, so any choice that has this in it has to go. That wouldn't be the right answer. All right, so this one's out. All right, now it looks like the one below that is just what you would get if you took this positive f of x and swapped it with the negative g of x. So algebraically, these are the same thing. So this one's out too. All right. So then we got the other two possibilities. I have a negative g here. I'm looking at two other integrals that are positive. I have a negative g, and in my two other integrals, my g of x is positive, so maybe that means I just got to factor out the g. So if I factor out the negative. So if I factor out the -1 and bring it on the outside, that would give me a positive. Right? The two negatives would make a positive. Integral over the interval of 2 to 1 of g of x minus f of x dx. All right, and so that would make the second choice equivalent. So either it's the first one or none at all. All right. So looking at all the different variations of this integral, I can't really think of doing anything else, but I also can't think of a universe in which I would have an f of x minus g of x or a g of x minus f of x, and somehow that becomes addition. Right. So this one would have to be the one that's not equivalent. The other thing that you could do, and it's kind of a lost, I don't want to say a lost art because I don't want to be too dramatic about it, but you could make up an f of x. Keep it simple. Let's say f of x is equal to x squared. That's if you're not really sure about the properties. All right. F of x is equal to x squared. All right. And let's say g of x is equal to, let's keep it positive. Let's say g of x is equal to just x. All right. And just see what happens. Integrate this over the interval of 1 to 2. you get some value, and then you try the other possibilities. So I'd duplicate this and try it with a plus sign. And I see I get a different result. Right? As opposed to, for example, the second choice, I'll just duplicate again, which would have been g of x minus f of x over the interval of 2 to 1. I mean, it's tedious, but you see it gives the same value. Right? It gives you the same value for the original integral. Right? So we're not proving anything, but we are creating a demonstration. It's just like properties of numbers. If I'm not sure, like let's say the commutative property, like of addition, 2 plus 3. If I'm not sure what that rule is, I would make up a couple of numbers and see what happens. 2 plus 3, all right, is that the same as 3 plus 2? Yes, okay, so I guess that's the commutative property of addition. That's all it's really getting at, right? With technology, the properties of integration, I mentioned this when we were talking about it for the first time, the properties of integration are a lot easier to handle because the calculator will do a lot of it for you. Now, L'Hopital's rule is one thing to find a derivative. It's another thing to find that derivative using L'Hopital's rule, right? So the process that we learned in class, I'll write it out, always involved us, did this a bunch of times, making the direct substitution first. So natural log of infinity over infinity would be an intermediate step, but that's really infinity over infinity. And we needed that indeterminate form to determine that L'Hopital's rule applies. So remember, I would write this a lot. I would write LHR applies, right? Because that's an indeterminate form. So A and B should have been infinities, right? But Blackboard's pain, so you just write I and F, all right? Once you recognize that L'Hopital's rule applies, you take the derivative of the top and the derivative of the bottom separately. Derivative of natural log of x is 1 over x. The derivative of x is 1, so that would be these entries. And then we'd apply our limit, right? So this would simplify down to the limit as x approached infinity of 1 over x. When I applied my limit, I'd get 1 over infinity, which equals 0. And so that should be my answer. Okay. Now, it is something that you could determine the answer to graphically. F of x is equal to ln of x over x. Take a look at the function. And as x goes out to infinity, decide or determine where y is going. It looks like it's going to the x-axis, which has a value of 0. So you'll get the answer. It's just everything else before that is what constitutes L'Hopital's rule. Right. The next question, it was a gift on the last test. It'll be a gift on the final. Can't promise it's going to be right rectangular approximation, but in the world of gifts, that's a small concession, right? Because it could be left. I mean, bottom line is you're using the program that program's a funny word, but at least in this context, you're using the Desmos that I created to do the computations here, right? I mean, unless you want to do it by hand, I can't imagine that's the case. I'm just gonna move this over a little bit so it's easier to get in there. Because I put this dummy function in there. I mean, it's a wonderful function. It's just not relevant to this problem. All right, so we have x root 9 minus 5x squared over the interval of 0 to 1. All right, with 4 subintervals. All right, so this is what our graph would look like. We're asked for right rectangular approximation, which is what I have it set to. So that's nice. All right, you can toggle back and forth. Well, you don't need to decide computations, but really we just only focus on LRAM and RRAM. This one calls for RRAM. And so that gives us 1.499. Nice and easy. All right, so Desmos work does it for you. You know, we did this enough, drawing out the rectangles and coming up with the values, that it was like, you know, like what purpose would it serve to have you do the computations by hand? I don't know, maybe a purpose, but I can't think of one. Right? So I let you off the hook with that, let you use the technology. And that would be the case even if this were in person, you know. So it is what it is. But then we have the mean value theorem. And you know, like for every question like number 3, there's a question like number 4, which requires you to do the extra stuff. All right. Still has the directions from the unit test on there, but you can just ignore that. So show that the function satisfies the mean value theorem over the given interval. Well, condition for the mean value theorem is that it must be continuous and differentiable on the given interval. All right. So I need to make sure that's the case, because it's possible that the mean value theorem doesn't apply. So I'm going to pop in an f of x equals 17 over 11 times the natural log of x squared plus 1. And then I'll restrict the domain by opening those squiggly brackets and typing my domain in inequality notation. -3 less than or equal to x less than or equal to 3. All right, just so I'm only looking at the relevant part. So what they want is first for us to determine if it's continuous and differentiable. Well, I don't see any holes or asymptotes or any other kind of gaps. Doesn't come to a point anywhere. I was suspicious about this location, but that seems to be rounded out. So it looks like we're in good shape. All right. So it is continuous and differentiable on the given interval. Now I need 2 things. I need to know what f of b minus f of a is over b minus a. And that's got to be equal to f prime of c somewhere over this interval. All right, so f of -3 minus f of 3 over -3. Oh, sorry, did it backwards. Classic Bob. All right, and then f prime, well, f prime goes back to the original function. F prime of x is equal to, well, we have our constant multiple 17 over 11. The derivative of a natural log is 1 over whatever's on the inside multiplied by the derivative of whatever's on the inside. The derivative of the inside is 2x. So that would be 2x over x squared plus 1. So the result of this computation here is going to be set equal to 2c, because we're finding f prime at some constant value c, over, so 2c over c squared plus 1. And so we'd solve this equation. So first I'd get my f of 3 minus f of -3 . over 3 minus -3. Well, that's just a 6. I'll just pop that in there. So we get a 0, which is really nice. All right. Can't guarantee that that's always going to happen, but when it does, it's beautiful. I'll actually just continue it on over here. 0 equals 2c over c squared plus 1. When you cross multiply, you get 2c equals 0. So the value of c that satisfies the mean value theorem over this interval would be equal to 0. Right. Now, it's not a guarantee that the average rate of change, the f of b minus f of a part of it, would be equal to 0. So you just got to be prepared for that. But in this case, it did. So that made this consistent with Rolle's theorem. But they didn't ask us about Rolle's theorem, so we don't have to address that. Right. But in number 5, they do ask about Rolle's theorem. So one of the conditions for the mean value theorem was, or the condition, the main condition, was that it had to be continuous and differentiable on the given interval. That's the same for Rolle's theorem, but also f of b has to be equal to f of a, or f of a has to be equal to f of b. Doesn't matter. Equality is commutative, so it doesn't make a difference. So I would need to compute f of 0 and verify that it's equal to f of pi over 2. All right. So plugging in a 0 to this function here, if I replace the x's with a 0, for cosine, that'll give me something other than 0, but for sine, it'll actually give me a 0. If one of the factors in a product is 0, the whole thing is 0, unless it's undefined or something like that. Cosine of pi over 2 is equal to 0, so square it, it's 0. And so again, one of the factors in the product is equal to 0, so the whole thing is equal to 0. So the condition is satisfied. So now what I would need to do is find the derivative of this function and set it equal to 0, and then use that to solve for x. All right. So there's 2 ways to handle this. One would be to use Desmos, but how you craft your answer on Desmos matters. If you just put the function and the derivative in there, you haven't really told me anything. So I'll just show you. Like, you can get the solutions. I'll just type in f of x is equal to 2 cosine squared of x times the sine of x. So we have that function. That's great. Restrict the domain. So over the interval of 0 to pi over 2. So we have that little teensy tiny little graph, which I can make a lot bigger. At 0, the result is 0. The f value is 0. At pi over 2, the result is also 0. So that's one of the conditions for Rolle's theorem. Now, I'm looking for the instance in which the function has a derivative equal to 0. So there's 2 ways to handle that. One, I just tap on the turning point, 0.616, and call it a day, or at least for one of the solutions. There's 2 of them, as it turns out. The other would be to have Desmos determine the derivative over the interval and take note of any instance in which the derivative is equal to 0. That happens here and here. So you get your solutions, but the thing is, if you just submit this to me, you got to understand these values aren't staying on the screen. So if this is your supporting work on Desmos, here, I found the answer, wonderful. Just understand that when you send it, I'm seeing this, which is showing a function and its derivative graphed. It's not giving me any other information. So what I'd have to do is manually type in the 0.6155, 0, label it up so that it stays there. And then the same thing with the pi over 2, 0, label it up so it stays there. So now I have some supporting work, but I also have to state what the final answer is, you know? Now, if you're doing it by hand, so you'd state that all in the Desmos before submitting it, right? But if you're doing it by hand, you'd have to use the product rule, or you don't really necessarily have to. There's other ways to do it. One way would be to use a trig identity, but I believe, if I'm not mistaken, that trig identity approach still involves a product rule in some capacity. But regardless, one way or the other, no matter what approach you use, it's still going to have some oomph to it. So if we just do it as is, f prime of x would be the first function, 2 cosine squared x, times the derivative of the second, which is cosine x, plus the second function, sine of x, times the derivative of the first, which is 4 cosine x, times negative sine x. All right, we do a little shrinky dink here. Well, actually, I'll leave that one alone, that part of it alone. All right, so this derivative would then get set equal to 0, and you would solve from there, but it kind of makes sense to simplify it a little bit first. You know, this would be 2 cosine cubed x minus 4 cosine x sine squared x. All right, set that equal to 0. We have a common factor here. We can pull out a 2 cosine x. That'll give me cosine squared x minus 2 sine squared x. All right. Set each of those factors equal to 0. You'd have 2 cosine x equals 0. And then cosine squared x minus, I'm going to bring it in, 2 sine squared x equals 0. Okay. The 2 cosine x equals 0, that could be thought of as cosine x equals 0. On this domain, the only time that happens, the only instance for which that happens would be x equals pi over 2. So that's one of our solutions. That's good. Now for the other one, you have some more work involved. So now, I mean, it's really just a matter of which approach you want to take, but I'll use the trig identity one way or the other. In this case, I'll replace the cosine squared with a 1 minus sine squared. Minus the 2 sine squared x that's already there equals 0. So 1 minus 3 sine squared x is equal to 0. So 3 sine squared x is equal to 1, which means sine squared x is equal to 1/3, which means sine of x is equal to, well, plus or minus the square root of 1/3, but we're only in the first quadrant. Right, so I would only care about the positive square root. And so if I take the inverse sine of the square root of 1/3, right, I get my 0.616 that way, right? But if this serves as anything, it's probably more of a deterrent for you to do the problem this way than it is for you, motivation. And if you could do it with the Desmos approach, that's probably the way to go because it'll save you all this time. Right? So that's my recommendation. It's just how you craft your solution on Desmos that matters. All right, but you have your two values, pi over 2 and 0.616. Now, number 6 is saying state the derivative, a little bit of chain rule there. So I have an outer function, 3 something squared. So f prime of x would be 6 times that something to the first power. That something is tangent 3x. So then we take the derivative of that. The derivative of tangent of some function would be secant squared of that function. That function is 3x and has a derivative of 3. All right. So this one's not bad. I mean, I guess it would be a lot worse if you had to simplify it, but you don't have to. So there you go. The next one is an implicit differentiation question. So it was a ordering question previously, but that's not a guarantee that it'll be an ordering question on the test. I usually like to get an ordering question in there somewhere, but we'll see. When we're applying the method of implicit differentiation, you just remember you take the derivative as you normally would, except anytime you take the derivative of a y term, you slap on a dy dx. All right. There's more theory to it than that, but we're in crunch time now, so we're going to just get down to business. So I have two terms here, or two factors, I should say, because that would be the right thing to say. 3x and y. So first times the derivative of the second plus the second times the derivative of the first. All right. So that takes care of this whole pair of factors, I guess you could say. Then the y squared becomes plus 2y. Derivative of y squared is 2y, but because it's a y term, dy dx. And the right side just goes to a 1. All right. So in terms of just matching up with the options here, what we just wrote would correspond with this one here. So this would be our first one, our first step. Then looking at what played out from there, the next step seemed to be just kind of cleaning things up. So we'd be looking at 3x dy dx plus 3y plus 2y dy dx equals 1. All right. So that's not a choice. So the next step must have been to get rid of that 3y because we want to isolate the dy dx. So we're looking at 3x dy dx plus 2y dy dx is equal to 1 minus 3y. So that makes this our second step. I mean, honestly, the one where it says dy dx equals, I mean, if that's not your final answer or the last step in the process, then it has to be the mother of all trick questions. And I don't do trick questions. So that's going to be step 4. So we already have the answer, but we'll just carry it out to review the process here. So I have a common dy dx. Pull it out, we have 3x plus 2y, which makes this our third step in this progression. And then the last thing to do would be to get the dy dx alone, and that would only happen if we divided both sides by the 3x plus 2y. Which would make this step 4. So when you're differentiating using the implicit differentiation process, it's really a little bit of calculus, a whole lot of algebra. But that first step is the calculus step, the part where you actually differentiate. The rest of it is getting it into the appropriate form, which is all algebra. Right. It's honestly, I mean, this doesn't make anybody feel good when I say it. It's all pretty basic algebra, but the notation is crazy. So it makes basic algebra look way more complicated than it really should. All right. Number 8 is just a limit question. All right. Now you could use L'Hopital's rule for this, but it's not a L'Hopital question because I didn't say use the method of L'Hopital to get the solution. I just said find the limit. All right. And on the test, on the final exam, that's how number 8 will be. You could use any method at your disposal to come up with the answer, whether it's a graphical approach or a L'Hopital's rule. It really doesn't make a difference. So I'll do it both ways. All right. So on the calculator, if I put my function f of x, sine of x over 2x, as x approaches 0, so that's going to put me right on the y-axis. It says undefined, but graphically, based on the scale here, that looks like a 0.5, right, or a 1/2. So I have my answer, because from both directions, we're approaching the same location, so it wouldn't be a DNE. There's no conflict there, right? But if I want to use L'Hopital's rule, or at least some other analytic approach, the first step would be to plug in the number, the limiting constant. So that becomes sine of 0 over 2 times 0, in which case we get 0 over 0. So indeterminate. L'Hopital's rule applies. Right? If you got something that wasn't indeterminate, then and it still didn't give you a solid answer, you wouldn't use L'Hopital's rule, but you would have to do some other method, like some other algebraic approach. Right? But because L'Hopital's rule applies, I'll differentiate the top and bottom. So I get cosine x, I got a 2, reapply my limit. So cosine of 0 over 2, cosine of 0 is equal to 1. 1 over 2 is 1/2. Now, because number 9 was a multiple choice question, you could get away with doing it as a, graphing calculator kind of deal. The one thing I would caution you about is if it's not multiple choice, you got to show some work. Yeah, you could get a graph out of it, but what if you need to compute a derivative? So let me take you through both ways again. So never a bad idea to pull up the graph just so you know what the answer is supposed to be. All right, just make sure you're only considering the graph over the appropriate domain. All right, because you look at this, it's kind of crazy. But if I only look at it over the interval of -3 pi over 2 to +3 pi over 2. You see, I'm only looking at these two pieces here. I got a relative max at -pi, -2. All right, so that's a relative max. All right, -pi, -2. And a relative minimum at pi2. All right. So far, choice 1 looks pretty good. I don't have relative maximums at pi, 2. So that wipes out all these other choices. And there is no absolute max or absolute min, because this graph, whether it's on this domain or an infinite domain, has vertical asymptotes, which means it goes up and down forever. All right. So there is no absolute extrema. All right. So You can get the answer that way, at least the relative part of it. Well, you could also get the absolutes too. But if you wanted to do it analytically, f prime of x, derivative of cosecant is negative cosecant cotangent. So -2 cosecant 1/2 x cotangent of 1/2 x times the derivative of the inner function, which would be a 1/2. So that would simplify. It's going to simplify to negative. I'll write it as cosecant first, but then we're going to kick it over to sines and cosines. Cotangent. Cosecant is 1 over sine. Cotangent is cosine over sine. So -1 over sine 1/2 x times cosine 1/2 x over sine 1/2 x. All right, so simplify a little bit more. We'd have negative cosine 1/2 x over sine squared of 1/2 x. All right, so that's what my first derivative would be equivalent to, f prime of x. I want to set this equal to 0, and under normal circumstances, I would set it equal to 1 over 0 as well. But those denominators, that sine squared 1/2 x, that would give us denominator of 0 under a certain circumstance, those are just giving us the vertical asymptotes in the graph, right? And that's because our original function was, it was 2 cosecant 1 over x, but it's really 2 over sine of 1/2 x, right? So what would have given us the vertical asymptotes for the original function would also give us the locations where the first derivative is undefined. And since that's the case, we know that the reason the first derivative is undefined is because of those vertical asymptotes. Therefore, it's irrelevant. And so when I set this equal to 0, that'll give me my critical values. And those are going to be the only critical values, right? The only relevant ones over the interval. All right. So I can divide both sides by -1. I get cosine 1/2 x is equal to 0. Now, under normal circumstances, I'd be thinking about, okay, well, where in the unit circle is cosine equal to 0? Well, it would be equal to 0. I'll just say cosine of x is equal to 0 on the unit circle at x equals pi over 2 and 3 pi over 2. All right. So that's what I would be thinking. But this isn't the cosine of x equals 0, it's cosine of 1/2 x. All right, so that changes things up a little bit. All right. So, but I could use that information because I know that this needs to result in a value of pi over 2 in order for this to work out. All right. So if it's resulting in a value of pi over 2, then I would take the 1/2 x and set it equal to pi over 2. And that would give me x is equal to pi. All right. But the thing is, there's other instances. I mean, we're not limited to one turn around the unit circle. You can see in our domain that we're going into the negative unit circle also. We're going into the negative theta realm, if you will. So from 0 to -2 pi. All right. So I would also include negative pi over 2 and -3 pi over 2, because those would be consistent with this domain. All right. So if I set 1/2 x equal to 3 pi over 2, that would give me x is equal to 3 pi. That's out of the domain, so therefore irrelevant. And that would actually knock out the -3 pi over 2 also, because that would just give me a -3 pi. All right, so these are irrelevant. But if I take 1/2 x and set it equal to negative pi over 2, I get x is equal to negative pi. That falls in the domain of negative 3 pi over 2 to 3 pi over 2. So that's a good one. All right. So then I would just want to know, okay, well, one's a max and one's a min based off of the way the question's structured. So plug them into the original function and see what they give you. That's in lieu of making a sign chart. So if I put in a negative pi, I get a negative 2. All right. So coordinates negative pi, negative 2. Versus pi comma 2. All right. So then we would just have to, I mean, you could look at the graph at this point. You know, we've done all the analytic stuff, or you can make the sign chart if you want, but one way or the other, you would want to make a distinction between max and min for these two coordinates. If you make the sign chart, that's the most analytic way of doing it, but it's also the most time consuming. Right? So that part is, you know, not always the most desirable approach to use, but these would be the two values, the two relevant values. And you would know that going in if it were a multiple choice question, but if it's not, then you would need those numbers. This would be how you'd get it. All right. So number 10 is supposed to be a gift, right? It's a gift on the practice test. It'll be a gift on the final. It's just saying find the derivative at a particular value. All you have to do, I mean, unless you want to compute the derivative by hand, which, I mean, it's your choice. Go ahead and do that if you want. I'm saying you don't have to do it, right? So you put in your original function and then evaluate that original function at the given number, in this case, pi over 4. All right, so that would be it. All right. So yeah, I mean, there's little things like, you know, making a sign chart for number 9. You know what? Let me just do that real quick. All right. So just so you have it. It's not a hint or anything. It's just in the spirit of you're going to need this going into Calc 2. I might as well just do it. One last review thing. All right. So we have an interval going from negative 3 pi over 2 to negative pi. We would stop at negative pi. Then we go from negative pi to pi. Right. There was an asymptote along the way, so we would actually include that also. So let me make some more room here. I'll shrink it down later. All right. So yeah, there was if memory serves, there was an asymptote at 0. So we would stop at 0, then go from 0 to pi, and then stop at pi, and then go from pi to 3 pi over 2. And so we would evaluate our derivative and draw some conclusions at these locations. If it'll lock in, doesn't want to lock in. And then it froze. It'll erase though for some reason. I don't know. I don't know what's going on there. Okay, that worked for some reason. So make a little table out of this. And the whole idea is to just verify that at negative pi, we're looking at a relative max. And at positive pi, we're looking at a relative min. So we would take any number that we could think of between negative 3 pi over 2 and negative pi and plug it in for the first derivative. So let me go back to that original function of f of x is equal to 2 cosecant 1/2 x All right, so that was the original function. Now I won't restrict the domain. I'll just pop it in. All right, so this is my derivative function in its full glory. If I take a number between negative pi and negative 3 pi over 2, like for example, it really doesn't matter, but I'll say like negative 5 pi over 4. I get a positive number. If I put a number between negative pi and 0, like negative pi over 4, I get a negative number. So it's increasing, decreasing. So that would be a relative max. We know that this one's a vertical asymptote. Then I could do the same thing for like pi over 4, which gives me a negative, and then like 5 pi over 4, which would give me a positive. So decreasing, increasing, which would be a relative minimum. All right. So that gives us an indication that there's a relative max at negative pi comma negative 2, and positive pi comma positive 2 would be the relative minimum. Although I'm pretty sure, just looking at it now, that there were a couple more asymptotes in there, but that's the general gist of it. Right. So I'm going to stop the recording.